And welcome to 2D1 video notes. Just to start off with, we're going to answer the question, what is a projectile? And, well, I probably mentioned it in class, but I'll give you a hint. This is the force diagram for it. That's it. So what's a projectile? Well, it's something that the only force is the force of gravity. If in the real world there is a little bit of air resistance, so generally we're going to ignore air resistance, and we're going to say for most objects that we're dealing with in this unit anyways, air resistance may be present, but it's so small where it doesn't make a significant difference. Some things about a projectile that we're going to notice is that as a result of this force of gravity, it is always accelerating downwards. You know what I'm going to try to do? I'm going to try to be consistent, and I'll make my acceleration in red here. So this will be an acceleration vector. The acceleration is always 10 meters per second squared downwards. The other thing that's important that we notice is that the horizontal velocity is constant. Okay, so let's start off with a little example here about a ball rolling off of a flat table. So we'll very quickly say, okay, so if here's the floor, then we've got a table up here. Okay, so there's our table. Maybe I should make it a little bit larger there. Okay, so there's our table. So we have a ball, so it's rolling forwards. Well, if it's going to end up here before it takes off, actually I need a different color, don't I? If it's going to end off there before it takes off, I'll just back up here. Before it rolls off, it's just going at a nice constant velocity forwards, isn't it? Look at that. And then after it rolls off, well, it'll go 2 forward and maybe 1 down, and go 2 forward and 2 down, and 2 forward and maybe 1, 2, 3 down. So you'll see this shape to it. It's not a straight line. The shape would be, it's moving forward, and then it's the right side of a parabola. The right half of a parabola. So if I was to draw the vector arrows for this, I can draw, I'm going to separate between my x direction and my y direction. So in this case, they're just going only in the x direction. Maybe I'll zoom in a little bit here. Only in the x direction. And so these are all Vx, because they're only in the x direction. Now as I continue along, this continues the v-axis. It's still going to the right, the same speed, the same velocity. In this case it's like the arrows stay the same length. But in my vertical direction, so that Vy would be 0 to begin with, here now it starts moving downwards. And this is growing. This one is growing. It hasn't quite hit the ground yet. So you'll notice that the horizontal velocity stays constant and the vertical velocity is accelerating downwards. It's changing all the time. I'm just going to find another place to write a little bit here. The results of our lab, we talked about the difference between the horizontal motion and the vertical motion, or the x direction and the y direction over here. So this is the horizontal motion. Usually maybe we'll say to the right is positive. Vertical really depends. Sometimes we're going to say up is positive. Sometimes we might say down is positive. I think in our lab we said up was positive. So what did we got? We had a position time graph that kind of went like this, xt, and we had a velocity time graph, and I'm going to say Vx, which was constant. So just like in our arrows here, each of these green Vx arrows are the same length, which tells me that this velocity was the same the whole time. For our vertical, we had a nice parabola that I guess it kind of looks like that, depending on some of your data might a little bit been different. And then our velocity in the y direction, so our Vy, it was thrown upwards, and it went like that. So here's where it was going up quickly, here it was at rest, and here it was going down quickly. The example from my ball rolling off the table would kind of been like this section, right? Because it's going, first it was had a vertical velocity of 0, then it's slow, faster, faster in the negative direction, in the downwards direction. So it kind of would have just been that section. Okay, here's your turn. I would like you to try for a ball thrown straight up. So I'll just say, well, it kind of goes up and then it comes down. So something like that. What I would like you to do is draw motion dots, and the only vectors that we need to do is the vertical. And actually, as a hint, maybe you do your dots straight up, but then if you come down, they'll be the same. So go up along one line and then come down on another line, and then try that out. Okay, so I'll give that. I want you to hit pause now and try that on your own. Okay, I got my answer half done here, so I'm throwing it up really quickly to begin with. So this is like after the ball's left my hand, and so it's going up quickly, then it's going up slower, going up slower, going up slower. These are my velocity vectors on the way up. At the same time, I can do the same thing but have acceleration vectors. So if I kind of do the same thing here, going on the way up, I'm just doing a little parallel version, but now I'll say, okay, now my acceleration the whole time is downwards. Here's my acceleration downwards. My acceleration is downwards. Acceleration is downwards. Acceleration is downwards. Okay, so now I'll draw my arrows for at the top. So at the very top, it's motionless just for an instant. And then now on the way down, you see the size of this up arrow should be the same as this down arrow there. Here, put this down further, and then these two should be the same, so those two are about the same, and then this one goes down, lots like that. So you'll notice that our old rules about when you have dots to always do halfway to the next one, that works great if you're going at a constant velocity, but when you're changing your velocity, sometimes it doesn't work exactly the same. So for this instance here, so here's an example where this arrow should be the same downwards as this one was upwards. So if these dots were each done 1 second, then here at this point the velocity would be 0. This velocity would be 10 up. This velocity would have been 20 up. This velocity would have been 30 up. This velocity would have been 40 up. And you can see that on the way down, this velocity would be 10 downwards. So maybe if we say that up is positive and down is negative, then that would be negative 20 here, because it's going 20 down, and here this is negative 30, and this is negative 40. You probably didn't write all that stuff down, but that's okay. And for our remaining of our acceleration vectors, it's pretty straightforward. We're going to say, oh, it's always going down by 10. So these values here are always 10 meters per second squared down. Okay, so that's what it looks like for a ball being thrown straight up. The velocity vectors on the way up, they're getting shorter because the acceleration is down. On the way down, the velocity vectors are getting longer because the acceleration is down. All right, so let's take a look at the next one here. How about for a ball that's thrown up at an angle? So this would actually be similar to what we did in our lab, right? So, well, if I start off, I'm going to say that we're going to start here, and I'm going to say that up is positive in this case. So yeah, maybe I'll go up 1, 2, 3, 4, 5, and over 2. Okay, so now I'm going to go up 4, 1, 2, 3, 4, and over 2. Oh, I'm going to go way up here. 1, 2, 3 and over 2, up 2 and over 2, up 1 and over 2. I'm going right to the top of the page. So you see the kind of pattern I'm doing. I'm always going over 2 to the right between dots, but I'm always changing the other ones. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5. So I end up over there. So I have a nice parabola here. If I was to sort of sketch it out, it's not a pointy at the end. It's actually kind of goes up. See if I can do a good job with this. Goes up here and just smooths out there and then comes down. See if I can make this work here. Something like that. Okay, so now if I want to add my velocity vectors, this velocity vector is always the same. The horizontal one, oh, I think I did too many on one of those there. I think I made a bit of a mistake. Okay, so this velocity vector is always the same. It's always moving to the right the same amount. And that is my Vx. Vx is always the same. Now my Vy starts higher. It's getting shorter. Getting shorter, getting shorter. At the top, there's only Vx, there's no Vy. And on the bottom, it's going downwards. And again, like this up, oops, I'm trying to highlight. Again, this up here should be this approximately the same length as that one down. I think I drew it too long there. So, and then this goes down, and then that one would go down as well. Maybe a little bit longer. Okay. Do you notice some symmetry to this? So, just like a parabola has symmetry. So if we were to do a, I'm going to say yes, we do. If we're going to take a look at this versus time. Let's say if we had, you know, this, and this graph here was meant to be time. If we are have this kind of symmetry, this would be halfway. So if this was 10 seconds, if I said something like the ball's in the air for 10 seconds, when is it at its highest point? 5 seconds, right? Unless you're dropping it off of a building or something like that, where it's going to fall, for, you know, more than from where you started from. What's interesting at the top? Well, at the top, the Vy is equal to 0. The Vx still constant. So whatever that value was, it stays at that value. Okay, so is that it? Okay, so there's no in-class mastery check. You can do the MOPS, VP7, VP8, VP9, and just a reminder, you go to physicsclassroom.com/MOP, and if you're going there, I think it's called Legacy MOPS, if you're going to just go through the website. You want to do it for credit mode. The teacher code is NMCS, and your student code is the one you've been using consistently. And then under mechanics, vectors and projectiles, so this would be sublevel 7, 8, and 9. And use Internet Explorer because it doesn't seem to work in other browsers. Okay, thanks, and I'll see you in class.